Hello students and welcome to Lesson 2 of Unit 7 Part 1. In this lesson we are going to learn to solve systems of linear equations by using graphing as a strategy. So our essential questions are: what types of solutions can a system of linear equations have, which we have already talked about in Lesson 1. We know that a system of linear equations can have one solution, no solution, or infinitely many solutions, which does not mean that it can be any ordered pair, but that there's too many to list, and we'll talk about what that looks like today. Second, we'll talk about why a system has a certain type. So why does it have only one solution? Why does it have no solution? Or why does it have infinitely many? And third, we're going to learn to use graphing in order to determine what type of solution a system of linear equations has. And we'll also be, if it is one solution, stating what that solution is. So to review and connect, in Lesson 1, we learned that a system of linear equations has two or more linear equations that represent a situation. We also learned that a single linear equation solution is all the points on its graphed line. So if you only have one linear equation like 2x plus 6y equals 10, this is linear because it's in standard form. If we only have one of these equations, if I graph it, however it looks, all the points on that line will be solutions that make this true. In other words, all the points are solutions to one linear equation. In other words, every point on here is a solution to this one equation. Now, a little bit new. Since a system of linear equations solution or solutions are the points that two or more equations share, graphing can allow us to see if the equations share only one point, all of their points, or no points at all. And I'll show you what that means in a minute. So in other words, once we graph them, we can see any of the ordered pairs that they share. So like we already know, there are three different types of solutions to a system. We might have one solution, infinitely many solutions, or no solutions at all. If there is one solution, the lines will intersect, meaning they will cross each other. Something like this. They will cross each other because they have different slopes. Because this one's going up, this one's going down, they will meet at one point. Lines that intersect, linear equations that intersect, will only share one point because they have different slopes. This one point, whatever it may be, x, y, is the only solution to the system that has one equation or one solution because they intersect. Now, there are infinitely many solutions when they are the same line. We also call that a coinciding line. This occurs because they have the same slope and y-intercept. The lines share all of their points, every single one of them. So for example, if I graphed the first one and it looked like this, and I went to graph the second one, it would look exactly the same. They would touch at every point because they are the same exact line. So every point on one line is the same as every point on the other line, and that means that every point on the line will make them true. And can we list every point on that line? No, so that's why we say there's infinitely many. We can't list them. And now last. The last situation where there's no solution is because of parallel lines. We will see that they have the same slope but different y-intercept. They will never share any points. So for example, if I graphed the first one and it looked like this, the second one would be parallel to it, so that they would never share any points because they're never getting closer together and will never get close enough to actually touch. So let's look at a graph. Here's a graph of a system. The two equations are y equals x plus 1 and y equals 3x minus 1. How many solutions would it have? Well, it would only have one solution because it only touches, the two linear equations only touch at one point. This is the only ordered pair that they share. So we would call this consistent because there is a solution and independent because there's only one solution. We know this because the two relationships only share one solution, one point. They cross at only one point is another way of saying the same thing, and that solution is the order pair 1, 2. Inputting 1, 2 into these equations is the only order pair that will make them both true. Everything else may make one of them true, but not the other. Now, in this picture, I have graphed two different lines. We have a red line, which starts here and goes this way with arrows on each end, so it keeps going, and a blue line right here. So how many solutions do we see this equation, these two equations having? Well, they have infinitely many solutions. Why? Because they're consistent and dependent. There's a solution. In fact, there's infinitely many. It's because the two relationships share every single ordered pair on their lines. And you can see that this is because they're coinciding. Look at their equations. Their equations are exactly the same. So everything that makes the first one true is going to make the second one true because they're the same exact equation. The solution? Infinitely many solutions. Every ordered pair on this line will make both of them true. So 3, -1 will make them true, 4.5, 0 will make them true, 6, 1 will make them true, and so on. Take a look at this graph. We have graphed this red line, which is y equals 2/5 x plus 1, and a blue line, which is y equals 2/5 x minus 3. As you can see, there's no solution. They do not share any points because they are parallel to each other. We would call this inconsistent because the relationships do not share any solutions. There are no ordered pairs that they will ever have in common because these two lines will never touch. Why? Because they are parallel lines. So the solution that you would write is there is no solution. The solution is that there is none. We are now going to start with a system of linear equations, graph it, and then determine the solution. So we're adding one step to the beginning of what we just did. Now we've learned that the best way to go from an equation to a graph is to use slope-intercept form because remember it's the most useful for graphing. So first we'll plot the y-intercept and then we'll move the slope continuously across the graph to create our line. So our first equation says y equals 1/5 x plus 2. So we'll start with our y-intercept, start at the origin, go up 2, and then move our slope, which is 1/5. So up 1 over 5. 1, 2, 3, 4, 5. And do the opposite as well. Down 1 and to the left 5. 1, 2, 3, 4, 5. Connect them with a line. And that's our linear function. Now, this is just one of them, the first one that I did, so I'm going to label it with a 1. Now I got to graph the second one to see where, if they do, they cross. So we'll start with y equals -2/5 x plus 5. Start by graphing the y-intercept, go up 5, 1, 2, 3, 4, 5. Move the slope down 2 over 5. So down 2, 1, 2 over 5, 1, 2, 3, 4, 5. So this linear equation is graphed like this. And we can see that they're intersecting lines. That means there's only one solution. And that solution is the point where they cross. So this point right here, where both the linear equations touch, that's our solution. Well, what's that order pair? 1, 2, 3, 4, 5, 1, 2, 3. This is the order pair 5, 3. And that's the only set of order pairs that will make these both true. So the solution is the order pair 5, 3. Let's try another example. Let's try y equals 2x minus 1 and y equals 2x plus 2. Again, they're already in slope-intercept form, but if they weren't, we can rearrange the equation so that they are. So let's start with our y-intercept. We have negative 1, so we'll go down 1. And our slope is 2, which remember is still a ratio, 2 over 1. So we're going to go up 2 over 1. So up 2 over 1, up 2 over 1, up 2 over 1. And do the opposite as well. Down 2, left 1, down 2, left 1 to finish our equation. So we'll start. Looks like that. Now let's do our second one. We have to start at the y-intercept, which is up 2. So this was our first one. Put a 1 down here. So our y-intercept is positive 2, and then we're going to move the slope, which actually is the same as the other one, up 2 over 1, which is going to give you a hint about them being parallel. Up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So this equation looks like that. As you can see, these are parallel lines, and I could tell that by the equations. They have the same slope, different y-intercepts, which is going to cause them to be parallel to each other. Parallel lines have no solution because they do not share any ordered pairs. They don't cross each other. So this has no solution. Now let's look at one that does not give us both equations in slope-intercept form. As you can see, the second one is not in slope-intercept form. We can get it in slope-intercept form, but we'll have to isolate the variable. So we'll add x to each side first, which we know is 1x. Negative x plus x makes 0, so we're left with positive 3y, or 3y equals positive x, or just x, plus 6. Now we'll divide each side by 3. This is shared division. So we have 1 divided by 3, x. So we have y equals 1/3 x. And positive 6 divided by 3, which is plus 2. And you can see right now, look at these two equations. They're exactly the same. So I'm going to graph the first one in red. I'm going to go up 2, because that's our y-intercept, and then I'm going to move our slope, which is 1/3, up 1 over 3, up 1 over 3, up 1 over 3, so it'll be like right here. Down 1 over 3, down 1 over 3, which would be like maybe right there. Connect them with a line. Okay, that equation looks like that. Now graph our second one. I'll graph it with blue dots. So I'm going to go up 2, and then I'm going to move my slope 1/3. So up 1 over 3, up 1 over 3, down 1 over 3, down 1 over 3. And you can see that if I draw a straight line to connect the blue dots, it's going to be the same as the one that connected the red dots. So how many points do these two lines share? They share all their points. So it's infinitely many solutions. All the points on the lines will make them true. If it makes the first one true, it will always make the second one true.